This session is dedicated to recurrent neural networks, another type of neural networks well suited for handling text data. We will see the different types of recurrent neural networks, RNN, architectures. We will also see the most important problem when training RNNs together with two specific units in RNN, GRU and LSTM. Several applications can also be found in the slides. RNNs offer a lot of flexibility. Here you have different types of input-output. The inputs are in red, the output in blue, and the hidden units of RNNs are in green. For example, 1-to-1 means that an output is predicted for each input. 1-to-many means that a sequence of output is associated to one input. Many-to-many means that a sequence of outputs is associated with a sequence of inputs with a none or positive delay. For each of the four types of input-output relations, can you find specific applications that fall into this framework, as image classification, for example? You can pause the video. One-to-one framework corresponds to a classic neural network. There is no sequential structure, so it can be used to predict house price, for example. One-to-many framework can be used to solve the problem of image captioning. For an image, a single input, you want to produce a sequence of words, commonly called a sentence, that describes the image. Many-to-one framework may correspond to sentiment analysis, in which the aim is to classify an input sequence, a text, depending on the positive-negative emotion hidden in the text. Many-to-many framework with a positive delay may correspond to translation, in which there is no one-to-one correspondence between words in different languages. You may need to look at several words before starting to translate a text. It could be difficult to grasp the full meaning of the sentence based on just the beginning of the sentence. Real-time frame labeling in videos corresponds to the last type of problems, the many-to-many framework with no delay, in which you cannot wait to see the next frame of the video to make a prediction. A real-time prediction is needed for each frame. In all stylized RNN architecture here, you see that you have just one hidden layer which is displayed in green. We will see that we can have more complex architectures. Note that here, each neuron, represented in green, is connected to the previous neuron of the same single hidden layer. This is a strong difference with classical neural networks. Indeed, in classic neural networks, neurons in a given layer do not communicate with each other. So why do we want to use RNN instead of classical neural networks, also called ANN, for artificial neural networks? ANNs can't deal with sequential or temporal data. Indeed, they can only take vectors of fixed size as inputs. They are not able to leverage on the intrinsic sequential structure of the input data. For example, the translation of a word strongly depends on the adjacent words in the sentence. However, in ANN, the order of the input variable is irrelevant to predict, whereas, of course, changing the order of the words in a sentence may dramatically change its meaning. That's why ANN are not suited for sequential data. Besides, the ANN does not implement the same operation for different elements of the input sequence. Even if it succeeds to translate the first part of the sequence, it may fail to translate the last part of the sentence. Indeed, the translation of different parts of the sentence may be performed in different manners in ANN. Since ANNs do not implement the same operation for the beginning and the end of the sentence, we can say that ANN lacks memory along the input sequence. Besides, ANN have a fixed structure which makes them not very well adapted to deal with data, inputs or outputs, of varying sizes. It is thus difficult to use them for translation, an application in which the length of the input-outputs vary drastically. There are reasons to believe that RNNs are more biologically realistic because of the recurrent connectivities found in the visual cortex of the brain.